So ladies and gentlemen, and friends and colleagues and honored guests, good evening and welcome to SRI International and the SETI Institute's presentation of the 2018 Drake Award. My name is Bill Diamond. I'm the president and CEO of the SETI Institute. The SETI Institute is a 501c3 nonprofit research, education, and outreach organization whose mission is to explore, understand, and explain the nature and origins of life in the universe and the evolution of intelligence. By virtue of your presence here tonight, you are now part of that mission. So welcome to the club. Before we get underway with official proceedings, I'd like to take this opportunity to thank our major sponsors and partners for the Drake Award, and especially wish to acknowledge and thank the University of Southern California and its provost, Michael Quick, for their lead sponsorship of the 2018 Drake Award. Michael is also a member of the Board of Trustees of the SETI Institute. Unfortunately, he was not able to join us this evening, but we're very grateful for the support of Michael and the university. I also want to thank the Breakthrough Prize Foundation and their fearless leader, Dr. Pete Warden, who is with us tonight. Hopefully many of you have had an opportunity to speak with Pete already. I'd like to thank Pete and Breakthrough for their support. And Bill Jeffries, who is the gracious CEO of SRI International, who are our hosts, for their generosity in providing these beautiful facilities, not only tonight, but to our regular monthly lecture series. Bill is not here tonight, but some of his colleagues from SRI are present here. I would like to also thank SETI Institute trustee Marco Larson, who's contributed generously to make this evening possible. And we had further board support from our chairman, Dan Langford, trustee Amaresh Kalapara, and yours truly kicking in here to make this event possible. So thanks to all our sponsors. And please thank me join me in thanking all our sponsors for their generosity. We really appreciate it. So. In addition to our guest of honor, who is Dr. Victoria Meadows, we have a number of other distinguished guests here this evening who will be participating in the program. First and foremost, the namesake behind the Drake Award, co-founder of the SETI Institute, author of the Drake Equation, astronomer, SETI pioneer, colleague of Carl Sagan, and otherwise splendid all-around guy, Dr. Frank Drake. If you have never heard of Frank, if you're not familiar with the Drake Equation, you can in the next few minutes leave quietly and we won't say anything. But Frank was also the first recipient of the Drake Award, though I understand that voting that first year was very close. The third recipient of the Drake Award, NASA scientist, engineer, and principal investigator for the Kepler Space Telescope mission, Bill Barucki, is also here this evening. Bill? Over here. He will join in the presentation of tonight's award. And personally, my feeling is the Kepler mission is among the most profound of all NASA missions ever launched, in that it forever changed our perspective on our place in the universe by discovering and teaching us that planets are everywhere. We didn't know that before Kepler. So, and not only was Bill really the father of the Kepler Space Telescope and really the initiator of the revolution of exoplanet research, but he also was one of the lead designers of the heat shields for the Apollo mission. So we're very honored to have Bill with us here tonight. Also joining us tonight, Penny Boston of NASA Ames Research Center and director of the NASA Astrobiology Institute. Penny, up here in the front row. Penny will be introducing Dr. Vicki Meadows. And then John Rummel is here. He's a SETI Institute scientist, planetary protection specialist, chair of our Science Advisory Board, and he will discuss the background and history of the Drake Award and tell us a little bit about that Drake Equation, which you see on your program. Dr. Jill Tarter, also a SETI pioneering astronomer, co-founder of the Institute, another contemporary of Carl Sagan and the inspiration behind Jodie Foster's character in the movie Contact, is here tonight. Jill? Let's see. Jill will be joined, before that, Jill is the Emeritus Chair of SETI Research at the Institute. She will participate in a panel discussion which will be following a talk by Vicki about her research. She will be joined by Dr. Nathalie Cabrol, who is the director of the Carl Sagan Center for Research at the SETI Institute. Nathalie, where are you? Here. They will be talking about Vicky's research, about astrobiology and exoplanets, in a discussion that will be moderated by the irrepressible Dr. Seth Shostak, senior astronomer of the SETI Institute, fellow of the Institute, and host of our signature science radio program, Big Picture Science. Seth, up here. Finally, I'd like to acknowledge and greet some special guests who are here with us tonight, including Dan Langford, chairman of the Board of Trustees of SETI. Dan. Dr. Pete Worden, former director of NASA Ames and present chairman of the Breakthrough Prize Foundation in the back. Pete, welcome. David Morrison, astronomer, planetary scientist, and senior scientist at the Solar System Exploration Research Virtual Institute at NASA Ames. Where's David? There he is. All right. Adam Tobin is the CEO of the Chabot Space and Science Center in Oakland, a good friend and colleague of ours. Adam. Also would like to greet and thank for being here tonight Andrew Simeon. He's an astronomer at UC Berkeley, a member of the Breakthrough Listen team, SETI team, and the new Bernard M. Oliver Chair of SETI Research at the SETI Institute. Andrew. And last but hardly least, our wonderful, amazing, but now sadly retired former Director of Education and previous President of the SETI Institute, Edna DeVore. Where's Edna? All right, so there are several other members of the SETI Institute Board of Trustees here tonight. They're all wearing a name badge that looks like this, so be sure to introduce yourselves and say hello. We're very grateful to have them here joining us this evening. We're also joined by a number of other researchers and staff from the SETI Institute and from NASA Ames. Pete Worden is joined by many members of the Breakthrough team with him tonight. We also have various guests with us from SRI International and the Chabot Center. So a special welcome to all these special friends and to all of you. And I'm speaking to you tonight on June 14th, which would be, had he still been around, the birthday of my father, who would have been 96 today. It's also Flag Day. It's also, I didn't know this until my son pointed it out, but it's also the birthday of the United States Army, which was born on this day in 1775. And son Christopher was a newly commissioned officer in the U.S. Army, so thanks to him for pointing that out. So an auspicious date, and also, and most importantly, the date for the celebration of the 2018 Drake Award. And with that, I want to bring John Rummel up to talk to us about the Drake Award and the Drake equation. John?
There are some signs up front here that say things like reserved speaker, and I'll try not to be a reserved speaker and actually say something useful. And I'll point out that Bill is a very thorough person in some ways, having given me an assignment to talk about the things he just talked about. Some of this might be duplicative, and I'll do the best I can. But in particular, I want to point out on behalf of Frank and myself that the Navy birthday is not until the fall, and I don't know what this Army thing is you're talking about. Sorry, Pete, I don't think you're old enough to have been in the Army. But the long and the short of it is that this is a great opportunity and a pleasure to be here today for an award that honors one of my favorite astronomers ever with a Navy background and pays the honor forward into the future. So later on, I'll ask Frank to stand up. I don't want to have him bouncing around all the time, but I really do want to ask you all to thank Frank again for what I'm about to say. The SETI Institute Science Advisory Board is responsible for advising the SETI Institute management and the Board of Trustees on the Institute's ongoing scientific agenda, including current and future research priorities, possible partnerships, and potential avenues for further funding. And together with the board is an expertise in all those Institute's ongoing programs, and a number of our members have extensive experience in areas related to the Institute's aspirations for the future. Some really excellent people are giving their time a couple of times a year to help the Institute. One of the more interesting duties of the board is that it recommends the recipient of the Institute's annual Frank Drake Award to the Board of Trustees. And this award has previously been given 3 times, as I think Bill could have ticked off, but I will point out that it's intended to be given approximately once a year to mark seminal contributions in the scientific study of the origin, nature, and prevalence of life in the universe, and for work on techniques for the discovery and the existence of such life. Things that are rising in prominence, not only in the scientific community, but this year in the Congress. Former recipients include Frank, as was mentioned, for his work at NRAO, the Arecibo Observatory, the Pioneer Plaque, and the working with Carl Sagan on things like the Voyager Golden Record, and doing a great job to bring that to the American public and the world public. Recipients have also included Charles Towns in 2002, the inventor of the maser and laser, for his work as champion of the optical SETI as well as radio SETI. Among other things, he discovered with Jack Welch water and ammonia in the interstellar medium, the first polyatomic molecules. With more than 200 now discovered, it suddenly made the universe seem much more bio-friendly. Of course, Towns also discovered a black hole at the center of the galaxy, which arguably made the universe seem a little bit less friendly. That's the way it goes. More recently, the 2015 award was given to Bill Baruchi, who's not only investigated Apollo heat shields, but later investigations about lightning strikes on Earth and how it could create organic precursors for life, certainly nitrogen and nitrates. And finally, he became the principal advocate of the Kepler mission, which, as Bill mentioned, has basically revolutionized our understanding of how many planets are there around other suns elsewhere in the galaxy. I believe these gentlemen together deserve a round of applause. Tonight, I'm also pleased to say that it is not a gentleman whose work we're acknowledging, and we'll get to that later. Even though I'm, thanks to Frank Drake, and in your program, you each have a copy of the Drake equation. And the Drake equation can be interpreted in a number of ways, but the Institute's programs can be organized around it as well. It's intended to estimate the number of civilizations in the Milky Way galaxy whose electromagnetic emissions are detectable, but which can also be a convenient way to understand the significance of various factors, the fraction of stars, the rate of formation of stars that's suitable for the development of intelligent life, the fraction of stars which possess planetary systems, the number of planets to be expected in any given solar system that have an environment or environment suitable for life, and the fraction of suitable planets on which life actually appears. The term F sub I is generally explained as the fraction of life-bearing planets on which intelligent life emerges, followed by the fraction of civilizations that develop a technology that can be detected, i.e. a technosignature. Those technosignatures are significant, but the award given today, we are looking at detecting biosignatures that are not necessarily produced by intelligent life. In fact, instead, they may be a result of the biochemistry of life working in an environment that may be unsuitable for life as we, humans, prefer it. Instead, our signatures reflective of life as it has happened, even without our science fiction tendencies. In that context, the term L, which here is the length of time such civilizations release detectable signals into space, could be recast in a different context. One that would be compatible with microbes or plants, and thus could be very much longer than the lifetime of our current civilization, or any conceivable civilization, and instead represent the lifetime of something as basic as the process of photosynthesis, once it has been established on an alien world around another star. Note that the term photosynthesis may not involve only green chlorophyll, as we demonstrate on Earth each fall, or even bring it with the release of oxygen. As humans, we have distinct limitations and don't get appreciate the benefits of using life, even the dim light from deep-sea hydrothermal vents, as a means for a cell to get free ATP. Yum. For our 2018 nomination for the Drake Award recipient, the Science Advisory Board has chosen a leader in the scientific estimation and detection of extrasolar life, conducting research to understand the factors affecting habitability and biosignature generation, working to provide for the robust characterization of terrestrial exoplanets to search for signs of habitability and life. Before we get to her, it gives me great pleasure to bring Frank Drake to the stage and have Frank tell us a few observations about astrobiology and SETI. Frank?
Well, thank you, John. When Bill first talked to me about speaking tonight, I asked him, what should I talk about? And he said, I think you need to explain what astrobiology is to this audience, because some of them aren't familiar with it. And that kind of shocked me, because supposedly everybody in this room is here because they're interested in astrobiology. So, but it could be that there are people who believe that astrobiology is just what its name seems to say, and that is, how do stars live? Is that what we're talking about here when we say astrobiology? What do you feed a star, for example? What kind of education do you give them? What is the biology of stars? Well, that's not what it's all about, as I think you know. Astrobiology is a topic which 20 years ago hardly existed. In fact, 40 years ago, it existed not at all, and in fact was a taboo subject, because although people had thought about intelligent life elsewhere, it was always harmed by poor ideas, phony observations, failed experiments. And so it had a very bad reputation. It was considered a bad thing to even contemplate extraterrestrial intelligent life. But long ago, back in the 1950s, it became apparent that there were technologies that no one had ever imagined, which had the capability of creating signals which could be detected across the great distances which separate the stars. And thus it became not crazy or ridiculous to contemplate that there might be signals, light signals, radio signals, bonfire signals, who knows, being used by stars to talk to one another, in effect. And so the subject came to be of interest. People slowly gravitated to it. Back in the 1960s, there were less than a dozen people who worked in the area. Today we have hundreds, even thousands, and it has become one of the principal activities of NASA. And it's not only of great scientific interest, just what biology might be elsewhere in the universe, but it is of popular interest too, because every thinking person, once they learn that there could be intelligent creatures on other stars or the planets of other stars, wonders what are they like. They can guess that their history would not be identical to our history, that their technology might be different. In fact, their biology itself might be very different. And so every thinking person, once they become aware of this, become interested in this subject. And that interest now has been carried over into support within NASA and other places of a great deal of work on this subject. And this is all related and contained within the concept of the word astrobiology. Now, at the present time, astrobiology is being pursued very diligently and with great effort, particularly by the United States. And we have been going about it in a very comprehensive way. Some astrobiologists work to study the processes by which life arises on a planet and to get an idea of where else it might arise and how often it might arise. That is work that is done right here on Earth. Others have already realized that we should search for life elsewhere in our solar system. And, and that has led to an expensive but very powerful, a large number of space missions which have gone to other planets searching for signs of life, either in existence now or having been existent in the past. And the places they have gone are becoming very more interesting the more we go to them, because we realize that there are places where life might have been or is now that we never conceived of, such as below the surface of Mars, in the soil, the wet soil that must be somewhere down below the surface of Mars. We've learned that there's an ocean on the satellite Europa of Jupiter, an ocean which has more water than all the oceans of Earth. And that ocean could well have creatures just as we'd have on Earth. There are two other oceans on the satellites of Jupiter where oceans may be present. We've learned that there is an ocean that no one ever imagined on the satellite Titan of Saturn, which is an ocean not of water but of hydrocarbons, things we burn to cook hamburgers and such things. We use butane and propane to make dinner sometimes. But that particular ocean is perhaps more suitable to the origins of life than the water ocean, which we believe gave rise to ourselves. We now know of an ocean elsewhere in the satellite Enceladus of Saturn, which could well be a place where life has arisen. And so there are these many things, many places, it turns out there are at least 7 of them, where there might be a different, entirely new, and very different form of life from the ones we are accustomed to on our own planet. And that has become one of the major goals of our search and what we do these days. And lastly, there are those of us who want to think about what is really the most interesting thing about life in space, and that is us, the intelligent life. Is there other intelligent life in space, and how do they live? What are their thoughts? What are their technologies? What are their ways of life? Do they communicate, and are they communicating or trying to communicate with us? And this is really the third major step that's being pursued in astrobiology, searching for signals, other evidence of extraterrestrial intelligent life. Now, I've mentioned these 3 areas of work, and all of them are being pursued at SETI Institute. It's the one institution in the entire world that addresses all of these very important, fascinating aspects of intelligent life in the universe. And I think the Institute can take pride in the fact that it has adopted all of these as things to support and to bring to successful discoveries if it can be done. So that's what astrobiology is all about, and I hope you know now a little more about it. Thanks. I had another mission. Ooh, well, I almost made a terrible mistake. I forgot to salute John because he outranks me in the Navy, but hi, John. See, I was so concentrating on what I was saying, I forgot I had to salute John. I'll do that. And then there's Penelope. And then there's Penelope. Which I was telling her when we were sitting here that we might be related because I have a 10 times great grandmother who was named Aunt Penelope.
I was looking a bit better than that.
But Penelope is the director of the NASA Astrobiology Institute, She's Penelope Boston. She's best known for crawling around in ugly caves. Beautiful caves with crystalline structures of great beauty and temperatures of unbearable amounts and dirty water and things like that. And inhabited water, yes, by creatures that don't exist anywhere else on Earth. So that's almost like discovering extraterrestrials. And she loves every minute of it, so she's going to speak to us now.
Well, I'm super pleased to be here for a lot of reasons. One is that many of you in the audience are known to me and valued by me in all different ways, and not the least of which being Frank, but I have to point out that he has another great accomplishment, and that is that he is the father of the great science writer Nadia Drake, of whom I am a great fan, so yay. Good work, Frank. My job is to introduce a young lady whose work I was familiar with before I ever met her. And one of the great pleasures that I've had becoming the director of NAI is to cross paths with folks that, believe it or not, I don't know everybody in the astrobiology community. And Vicki Meadows works in a very different area of the vast footprint of astrobiology than I do. But now we have come to know each other, and in many ways we're sisters under the skin. Because Vicki clearly has been drawn to the seductive but very challenging intersection of different fields in pursuit of nailing down what are the signatures of life. In Vicki's particular case, she's working in this amazing gift that we have of living in the era of exoplanets, knowing that they for sure actually exist, seeing more and more of them identified, and seeing more and more deep thinking about how do we interrogate these objects. And so with her own pioneering work, and from the point of view of the NASA Astrobiology Institute, essentially being one of the major creators of this new field of, I don't even know what to call it, exobioplanetology, or something like that involving a lot of syllables. This is a unique direction for us to go, and it is so tremendously timely. We obviously can learn a great deal from studying our own planet and our own solar system, but having the ability to reach out into the galaxy and have whole populations of objects, some of which may be life-bearing, and be able to study that in a totally different way, albeit that the data is very different from what we develop here. One of the things that bond Vicki and I is her dedication to being an educator. So those of you who know me know that I've only recently, in the last couple of years, taken this bureaucratic job at NASA. But for many years, of course, I was a university professor and educator, both in formal and informal ways. And so this deep dedication that Vicki has shown to her early career folks, the huge number of graduate students and postdocs that she has mentored. And when I say mentored, I don't mean in the usual minimal way that some advisors mentor. She really tremendously cares about her students, guides them, worries about them, and follows all of her chicks as they go on forward into their careers. And I think this is a tremendously admirable thing, because not only can we have the legacy of our own research as we leave our imprint upon the land, but smoothing the pathway for the generations to come in an enterprise as long-lasting into our future as astrobiology and the search for intelligent life, the search for exoplanets that bear life is critical. We clearly are not going to be able to do so much of the work that we have ahead of us as a species in our own lifetimes. And so this dedication to the future is a remarkable thing. From our perspective, of course, at the NAI, Vicky's team, the Virtual Planet Lab, is an amazing phenomenon. She's grown it from perhaps 15, 16, 17 members originally in 2001 to over 75 individuals at many, many different institutions, and interacted with other teams by way of exchanging senior scientists, early career people, hatching new areas of investigation, and tremendously pushing not only her own areas forward, but also contributing to this very wide variety. She spent her early years gaining her higher education in Australia, getting her PhD from the university in Sydney, where I too have many friends, and then came to the United States, and luckily we were able to corral her and retain her here. So with that, I want to introduce our Drake awardee, Dr. Victoria Meadows.
So this is the fun part, when we get to present Vicky with more stuff than she can carry off the stage. But after that wonderful introduction by Penny, a lesson in astrobiology by Frank, an overview of the Drake equation by John, let's have a big round of applause for the 2018 Drake Award recipient, Dr. Vicky Meadows. Here is the Drake Award for 2018.
And thank you so much for coming tonight to help me celebrate. I really appreciate that. So what I'm going to talk about tonight is just a sort of an overview of the Virtual Planetary Laboratory, which is my research group. It's both my research group and my team of work. I'm going to just give, I've got like 15, 20 minutes here, so I'll just give a little bit of an overview of, why I think the VPL is unusual and why I think it's special, and sort of some of the key results or the key areas that we work in that I think we've made the most impact in. So first of all, you'll notice that this talk is not just by me, it's by the Virtual Planetary Laboratory team, and I want to stress that, of course, one person cannot do all the work that the VPL has achieved over its last 17 years. And so again, I'll be definitely calling out the importance of the team here. So as a species, when we look up into the night sky, we have a lot of questions, a lot. We look up at those stars, and back eons ago, we wondered whether they were other campfires with other humans around them. We now know that there are other suns, and we now know, as was pointed out by previous speakers, that in fact there are lots of planets around them. And many of those planets are not like those in our solar system at all. And so as we look out into the universe, I think when we think about exoplanet science, we're governed by two principal questions. The first one we can all relate to, and that question is, are we weird? Okay? So this is the fundamental question of the field of comparative planetology. This is the question where we ask ourselves, this Earth on which we live and the life and this star, this yellow G-dwarf star, is this normal? Is this what we would expect for all these other planetary systems out there? We now know that that is not the case. We now know that, in fact, Kepler has done a fantastic job in showing us the census of planets that are very unlike planets in our own solar system. And so part of what we do in astrobiology as well is to try and understand the differences, not only in the different types of planets that might be out there, for example, very water-rich terrestrials, mostly unlike the Earth, or mini-Neptune planets that look like Neptune but are shrunk down to almost the size of an Earth, these sorts of worlds, but also trying to understand if there are habitable worlds out there. Are they different to our G-dwarf, nonetheless still habitable, but are there different modes of habitability? The second question, of course, we ask when we look out into the universe is, are we alone? So not only are we weird, are we typical for the different types of planets, but are we alone in the universe? And for me, in my field of exoplanet science, certainly we do wonder whether or not there are other intelligent species out there, but I also just fundamentally wonder whether life started out there anywhere else. I want to know if this is a living universe where there are planets everywhere that support life of some kind, even if that life is just pond slime. And as I often say to people, you know, in my field, in the exoplanet field, I'm not personally looking for little green men, but I am looking for little green microbes. And so that's what I'm trying to find. So when you try to find your little green microbes, you have to find a planet that's able to support liquid water on its surface. And even though life may exist in the subsurface, we want it on the surface so we can actually have a chance of seeing it with telescopes, because we do not yet have the capability to go to other star systems. Breakthrough Starshot's working on that, but until we're able to do that, for the time being, we must study these planets remotely using telescopes and try to understand whether there's life on them. So to give us a fighting chance, we want that life to be on the surface, in a surface ocean. We now know, and this was certainly not true when I started this in 2001, we now know that planets in the habitable zone of other stars are common. Maybe 1 in 4 M-dwarf stars has something that looks like about the right size as an Earth in its habitable zone. Where the habitable zone is that region where, you know, a planet could support liquid water on its surface. It's just the right amount of radiation from its star. And so that's incredibly exciting. But Kepler gave us this statistical result that, in fact, yes, these types of planets are common. What we need to do now to go that next step forward is to say, okay, well, they're common, but are there any nearby that we can actually study? And only in the last few years have we actually found these candidates to study, and that has been immensely exciting. And so we are now getting to know the neighbors. We are now looking at planetary systems that are close to us, within about 40 light years of us, and several of them have excellent candidates in them for further study. And so we're looking very much forward to the James Webb Space Telescope being launched so that we can start studying many of these systems in earnest. And we also have the possibility of being able to study these with ground-based telescopes as well. So there's going to be some very large ground-based telescopes being built in the next 5 to 10 years that may be able to take on some of these systems. So these are some of the superstar planets that we're looking forward to studying. The TRAPPIST-1 system, a system of 7 planets orbiting around a star, an M8 dwarf that is so small it's not very much bigger than Jupiter. So the star itself is not much bigger than Jupiter. It has Earth-sized planets orbiting around it. It's a fabulous system for astronomers because those Earth-sized planets make a big impact on the light coming from that Jupiter-sized star. And so that will be one of the sort of top targets the James Webb Space Telescope will observe. And of course, the Virtual Planetary Laboratory is very interested in modeling that system to learn more about it. We also know there is a planet in orbit around the closest star to our sun, Proxima Centauri. That one, unfortunately, doesn't transit in front of its star. We can't use that particular JWST technique on it, but there are other ways we can learn about it. And we have a bunch of other candidates planets as well, the LHS 1140b, very much definitely a rocky, solid planet in the habitable zone of its parent star. And so this is immensely exciting that we now actually have targets out there that are almost certainly rocky and within this habitable zone. So against this backdrop of all of these exciting discoveries in exoplanet science, and by the way, VPL was there long before many of them. We've been working really towards this time. And so this is a very special time for the Virtual Planetary Lab in the sense that we were always modeling planets and trying to understand what they would look like. And the team motto was always, planets are hard, which is a play on the term that terrestrial planets are rocky and hard, and those were the types of planets we cared about, so planets are hard. But also planets are complex and difficult. And so, you know, another one of our sayings, it takes a village to model a planet. So we really needed a lot of work to get into this. Now, though, the VPL's motto has changed. Our motto is now, following from Game of Thrones, photons are coming. Okay, so we've gone from a modeling-based group that started 17 years ago, now coming to this final crux of we are now going to start getting data on these types of targets in the habitable zone. So for the VPL, our question has always been, I just want to make sure we got this up here. So VPL's fundamental overarching question, which we've had from day one and we have kept for the last 17 years, is how would we recognize whether an extrasolar planet can or does support life? Okay, and if you unpack that statement, the recognize is really about what can we observe and understand about this system, and whether an extrasolar planet can support life, that's the habitability question, and whether or not it does support life is the search for life and biosignatures. So we have always been about how do we study these planets to be able to interpret their environments in such a way that we can tell whether they're able to support life or whether they already have life on them. So to address that overarching question, the Virtual Planetary Laboratory has been broken into 5 tasks. And when we set out to do this, this was really an impossible task. When we started this, when I started this group, back in 2001, extrasolar hot Jupiters had been discovered. People hadn't really been thinking at that time about whether or not, there could be habitable Earth-like planets. So we just decided to dive in with both boots on and say, okay, what can we do to set the stage now for ultimately that day when we finally do get habitable zone terrestrial planets to look at? So I came up with a stepping sequence of 5 tasks that I hope would get us there with the least amount of giggle factor possible, right? So I mean, again, as Frank was pointing out, early in these fields, people wonder if this is really science or not. So we started from the most defensible position of all, which was to study the Earth and to look at the Earth as if it were an exoplanet and try to understand the features in the Earth that could potentially be observed over very large distances. We then looked at the Earth through time, task B. So our modern day Earth is just one example of a habitable planet. If you go back through the history of the Earth, there are many, many habitable planets that look completely unlike the modern Earth, encased in the history of our world. And so, as one of my colleagues is fond of saying, the early Earth is the only alien planet for which we have biological and geological constraints. Our third task, task C, the habitable planet, is where we kind of stepped off a cliff. Before we were being constrained by observations and data, or going back through the rock record and looking at potential biological constraints as well. In the habitable planet, we started to model the interaction between the planet and its parent star and its host planetary system. And using computer models, coupled and very interdisciplinary, we started to look at those interactions to understand which planets were able to support life and which ones were less likely to do so. In task D, we moved beyond the habitable planet concept to the living planet to try and understand how life might leave a measurable global impact on its environment. So for astronomers who study exoplanets, that's our definition of a biosignature. Some phenomenon that is instigated by life that leaves a measurable global impact on a planet. Because again, we're trying to find life across 40 light years. Whatever it does has to be kind of obvious, or we won't be able to pick it up. And so in task D, our biologists, and there are several of them here tonight, I'll probably embarrass them later, are actually working in the laboratory and the field, understanding the sorts of byproducts you would get from different types of organisms and then feeding that into our models. And so these 4 tasks essentially help us generate different types of environments, different virtual planets. We then pass all of those the sort of environments that we develop from this through this 5th task, which is the rainbow on this slide here, the observer. And the observer then takes those environments, so by that I mean the temperature and pressure structure of the atmospheres, which constituents are in their atmospheres, what their surfaces look like, and we run it through we generate spectra of those environments, and we run them through instrument simulators, and we figure out if any of the upcoming missions can actually see the phenomenon we think are important in these environments. And so in that way, we couple the modeling that we do to these currently flying and future telescopes. So that's the VPL in a nutshell. That's what we do. So we take, again, things that we've learned about the Earth, the past, model understandings between star and planetary processes, life's impact, and we couple it through instrument simulators to try and understand what we might actually see. So I'm going to talk now just briefly about a few of the things that we've done that I think are kind of cool. So one of the first questions you ask is, is that planet habitable? How do we figure that out? And I always thought this was going to be a very complicated question where we would try and understand sort of the characteristics of the atmosphere and the star, and we would try and model it and figure out whether or not it could support conditions on the surface for liquid water. And somebody early on said, well, why don't you just look for an ocean? And I said, well, that's just crazy. Of course, you couldn't possibly do that. So it turns out that that actually might not be such a terrible idea. And so this was computer modeling that we did that was led by one of my students. And I'm just showing you the example of it here, but what we did is we showed that you could in fact pick the glint of the Earth's ocean out, even if you had collapsed the Earth down to a pale blue dot. If you couldn't see any spatial information, you could still pick out the glint from the ocean as the planet entered crescent phase. And you could discriminate it from forward scattering clouds. So clouds will tend to brighten the Earth as well as it gets towards crescent phase. So we showed that that was actually something that's potentially possible. And for some of the larger telescopes that we're talking about building in the future, we might be able to directly detect those oceans. So just to show you there, here's an example of things in our solar system, and another reason why VPL always likes to go back to the solar system for find examples. But if you look at Titan here in the near infrared, you can see glint from a lake, I think it's Kraken Mare, near the North Pole of Titan. And if you look at the circled image of the Earth there, if you can see that bright spot of light in the crescent shape there, then you have become a remote sensing ocean detector, because that is in fact the glint from the Earth's ocean being seen in that crescent. And so as you take the brightness of this planet, as it goes through its different phases, you could potentially detect an ocean. Another thing that we have been able to do is simply just generate spectra of what large telescopes might be able to see. This is a very messy diagram. What I want you to take away from, and again, spectra, only a mother could love. But these are simulations of what the light passing through the atmosphere of TRAPPIST-1e, so that is the planet that is most likely to be habitable in the TRAPPIST-1 system. We have simulated it for a bunch of different evolutionary scenarios. If it had its ocean boiled off, if it didn't, if it was able to outgas material into its atmosphere, if its mantle was desiccated. So able to run through different scenarios for what that environment might look like, and then model them as to what the JWST, the James Webb Space Telescope, might be able to see. And so that's very much the VPL sort of in full flight, understanding the possibilities and potentialities for the type of environment we might see, modeling it, and then figuring out if the telescope can in fact observe it. The other big question we like to try and address, and I think one where we've made some impact, is how should we pick the right planet to study? So when we only have a few targets, and some are more observable than others, we'll just go and observe the easy ones. But TESS is flying now, and it will find even more targets than TRAPPIST-1 and LHS 1140 and Proxima Centauri b for us to look at. So the question will be, okay, if we can only observe a few of these with JWST, which one do we actually pick? You know, which is the golden planet, as we like to call it. So one way of doing this is to try and understand all of those factors that actually affect whether or not a planet is habitable. And classically, you think of the habitable zone. And the habitable zone is figured out for a planetary system by looking at the type of star that you have and the distance a planet is from that parent star. And that's how you figure out whether or not it's in the habitable zone. But it turns out that's just really a two-dimensional slice through a much more complex parametric system of factors that actually affect whether or not a planet is able to be habitable. So if we take surface liquid water as our sort of standard, what the VPL has done is shown that, in fact, habitability depends on all of these different major components. One is the properties of the planet itself, which you would expect. You know, does it have water? Is it able to, does it have an atmosphere? Is it able to retain its ocean? But also how it interacts with its star, both radiatively, the UV radiation and protons, for example, it takes from its star, and gravitationally. How does the star actually affect the orbit of the planet, and is it able to flex the planet and actually warm it via a process called tidal heating? And then also the planetary system itself. Did the planetary system conspire to make sure that that planet never formed with water in the first place? Did it send Jupiter careening through the system? Did it, via a sibling planet, actually cause this particular planet to have its orbit always eccentric and always heated tidally by the star? So all of these factors we started to look at, and this is what we call the planets are hard diagram, because when you actually map it out, which we have done, it looks a lot like this. So I tried to put this in a proposal once, and I was crash-tackled by my team who said, "Are you insane? And nobody wants to see that, and it's terrifying, and put it away." So nonetheless, we have identified these things, and we are chipping away at them observationally, and also theoretically to see whether we can actually figure this stuff out. But the point is, for every one of these that we can characterize and understand the impact on the planet, we have a better sense of whether or not that planet can in fact be habitable. The other great thing, I think, that has happened, and just in the last couple of years, but we were kind of always building towards this, is that VPL has also been a bit of a downer, as it turns out, for biosignatures. But I think it's not so much a depressive force as we're kind of dragging biosignature science, kicking and screaming, into sort of a more mature state. And the reason I say this is just as with the simplistic habitable zone and then realizing, gosh, it's actually a lot more complicated than that, I'm sure you've all heard of oxygen as a potential biosignature. And you may have even heard that if we detect oxygen on another planet, then we're done. That's life. You go away, you pick up your Nobel Prize, everything's done. But it turns out that for our Earth orbiting our sun, it is very difficult to make oxygen any other way other than photosynthesis. But we started modeling processes on planets orbiting M-dwarfs, and this is something that happened actually in multiple areas of my team. The last couple of years, independent groups all came up with different ways that we could actually generate oxygen abiotically, so without life. So the initial reaction from the community was, oh no, you've ruined our best biosignature, and I had to repackage it and give it back to them and say, no, I've made your best biosignature even more robust, because now you can look for these mechanisms that could be happening that might be producing false oxygen, false positives for well, it's real oxygen, but the fact that it might look like a biosignature but isn't because the planet's actually producing it, that's what we call a false positive. So now VPL is mapping out all the potential false positives, and I've got a diagram up there of the sorts of things that we can do, which is, hey, if this process is working, for example, the planet just lost all of its ocean, and as a result, water was photolized and it built up a massive oxygen atmosphere. Turns out when you build up a massive oxygen atmosphere, different molecular bands appear in the spectrum because of O2 molecules bashing against each other. So we can look for that. We see oxygen, we say, great, oxygen, but is it due to ocean loss or is it due to photosynthesis? Let's make these complementary observations. So we have identified not just the false positives that get people depressed, but also the observational discriminants, the things that we should look for to try and figure this stuff out. So that's sort of the summary of the science I wanted to talk about. I do want to say, though, that again, all of this is done by just this amazing team. And that we are massively interdisciplinary. You know, some people talk about interdisciplinarity where they're talking about sort of two different branches of genome science or something. I am talking about, and this is something that Nikki Peronto, who's in the audience here, likes to talk about. VPL is actually, you know, coupling the microscope to the telescope. We're really getting people who work in very different fields to work along a chain that's something like, oh, hey, my microbe produces this gas. This person's model looks at how that gas affects both the climate and the spectra. You know, we then interact that with somebody else who knows something about the UV and tells us about the photochemistry on that molecule, and so on, and all the way to the telescope. So I do want to thank my team. They are amazing. They are the sort of people who, for example, they are biologists who are happy to talk to astronomers. That is rare and very valuable. And I just want to finish up here and point out that, yes, I do have an amazingly diverse team, but as Penny pointed out, I have an amazing group of young people who have worked on this team over time, and I do want to acknowledge them. So this is Dr. Jada Arney. She's a civil servant scientist at the Goddard Space Flight Center working on the LUVOIR mission concept. So she's trying to get a 15-meter telescope in space to look for biosignatures. This is actually her dream job, and she is incredibly good at it. And here she is standing in front of the James Webb Space Telescope. Eddie Schwiedemann is now working with the UC Riverside team. He is my biosignature expert. He is the person who looked at and determined the observational discriminants for false positives. Sean Donegal-Goldman was my postdoc. Sean is everywhere in astrobiology now. He has a talent for policy and a talent for organizing people, and he's done some fantastic science on alternative biosignatures. He started to come out with really new biosignatures. This is Ty Robinson, my first ever student, my scientific firstborn. Ty here, by the way, this is not Ty's kid. Ty doesn't have kids. But we were sitting at a restaurant in Bern one night, and a child wandered up to him and said, "Could you read The Hungry Caterpillar to me?" And he obliged, and so that's what happened. But that's just the kind of guy that Ty is. Ty was the one who worked on the ocean detection and glint, and who was also an expert in radiative transfer. Andrew Linkowski, an ex-police officer who's now working with us. He is an expert on climate modeling. He's the one who generated those TRAPPIST spectra that you saw. Jake Lustig-Jaeger, he is my connecting to the telescope expert. He is just fantastic at simulating observations and figuring out whether telescopes can actually observe them. Omawa Shields, now a professor at UC Irvine. She is an expert on climate modeling, especially for planets orbiting M dwarfs. Lupita Tovar, just a new student. She's in her first year, but she is a photochemist, and she is helping me try and understand whether JWST actually can see biosignatures in the atmospheres of planets like TRAPPIST-1e. And then I have Kim Bott here as a postdoc. She is an expert on polarization signals, which I know nothing about, and so she's been fantastic in helping me learn about how we might use polarization to detect oceans, to understand aerosols on planets, to figure out the composition, to look for rainbows in exoplanets far away. And I'm going to finish this off by actually thanking my admin team. It takes a village to model a planet, but somebody has to herd that village into submission. This is Dan Larson, who is our administrator for VPL. He is a two-tour Iraqi veteran. I found those skills to be particularly useful in managing my team. I have Andrew again, my ex-police officer, also useful, especially, as you might imagine, I like people who are disciplined, intelligent, and great in a crisis, because that happens a lot. And there's Jada again. And honestly, of the three people up there, she's probably the most dangerous of the lot. She is just a fantastic organizer of scientists and a cat herder. And so I use her a lot. She is my secret weapon. She will get in there and she will get people to do things that I have been having difficulty encouraging them to do. So those three people, and Jada is my deputy principal investigator. So those three people are particularly important to me in organizing what we do here. And of course, a final thank you to NASA, the NASA Astrobiology Institute, for all this funding over the years. We could not have done this without this massive amount of funding that allowed us to have this massive interdisciplinary team working in this area. And I would like to thank the SETI Institute so much for the honor of this award. I really, really appreciate it. And, but again, my team is amazing. And finally, I want to thank Ron, my husband, who has kept me alive all this time. I work very long hours. I travel a lot. He's always there, making sure I don't die. And for that, darling, thank you so much. So I will finish with this slide, just showing you the VPL at the moment. Those in orange are students and postdocs, or former students and postdocs of this program. And so you can see, again, the army of young people who have been trained in this area and come out of this, and they are all absolutely incredible. So with that, I will finish up here. So thank you very much.
Thank you, Penny. That was wonderful, and you can stay right here. I will make the observation that not only does it take a village to do this kind of work, but I did observe that the scientist with the biggest smile on his face was the one sitting at the bar. I don't know if anybody picked up on that, but in any case, an amazing team. That's right, that's right. And the only thing that we have really that could possibly even top the Drake Award is that people who come and speak with our audience at these SETI Talks get the rare but highly coveted SETI Talks patch, which I will now present to you. And if you're ever out and about and you see somebody wearing one of these patches, you want to bow with great respect, and you are now among that club of elite.
Thank you so much.
All right, so if I could have Seth and Nathalie and Jill join us up on stage for a panel discussion to talk about your work in a little more detail. Seth?
Great.
Nathalie?
I do not want to lose this.
Don't lose it, just leave it right there. We'll take care of it.
It's like a mic drop from orbit.
Exactly.
All right, we're going to have a short panel here. I noticed that they have all seated themselves as far as possible from the moderator.
We know better.
I don't know why that is.
We're all
And
very
it is
smart.
said that it's always a terrible thing to get between an audience and their dessert. That's what you have to look forward to after this. I am the moderator, although I have to say that I don't like discussions that are moderate. I think they're much more interesting if they're immoderate, so I hope you will not hold back. Actually, before I thought about what to ask you, I asked myself, where does the word panel actually come from?
Oh.
And yeah, it's not so obvious. It comes from Latin, as all the good words do, and the original Latin was panus, which means a piece of cloth, like a rag, okay? But that became a list because people would write things on it, and the list eventually became you. So I don't like to rag our panel, but that's what they are. Frank has already pointed out the intrigue of the word astrobiology, which, of course, you may note, has a mixed heritage, both Latin and Greek, which makes astrobiologists sound especially learned. Frank asked, he thought that astrobiology was how stars live, and I think that the obvious answer is, if you're the Kardashians, very well. Okay, enough of all that. Let's introduce the panel members. You've heard about them all. On the far side from me is Jill Tarter, more than a little well known in SETI circles, and currently a member of the SETI Institute's Board of Trustees. Jill Tarter. Next to her is Vicky. She requires no introduction, but I did get a copy of her business card, and it says, Professor at the University of Washington, Principal Investigator for the Virtual Planetary Laboratory, Lead Team of the NASA Astrobiology Institute, and the winner of an occasional award. That's a big card.
That's great.
Nathalie Cabrol here is director of the Carl Sagan Center for Research at the Institute. So let's get right to it. Natalie, big news from NASA last week, right? The detection of methane on Mars that seems to vary, and vary quite a bit, with the seasons. Tantalizing but indirect evidence that life might have been or could still be hanging out on our little ruddy buddy. So how excited should we be about this news?
I guess you should be very excited, but also very cautious because you can explain those signatures in a biological and abiotic way as well. I think this is great to see them, but by no means this is already an evidence that life is there. They can be really the result of a process that is geological and cosmic, but they also can be the result of a process that's biological. So interesting, but more data necessary.
Isn't that always the case? Vicky, did you want to say something about that?
No, I think that's an accurate assessment. And, I've just been talking about false positives, and yeah, they happen on planets even nearby. And so it's intriguing, but yes, I agree with Natalie that, more data is needed, and we need to rule out other processes that might be producing it.
So Seth, I have a huge necklace made out of serpentine, and I like to wear it to cocktail parties because it's a wonderful opportunity to talk to people about methane on Mars. Because the serpentization of olivine, a purely geological process, could be an explanation for the methane that we see. It does, however, require flowing liquid water. So it's not necessarily a bad or a dead end to the life story, but that might be a good alternative explanation.
I have to say, the cocktail parties you get invited to sound a little more cerebral than the ones I go to. Nobody ever asked me about the methane on Mars. But, okay, what about the chemicals that were also found with the Curiosity rover on Mars? Are those perhaps more exciting than the methane? The methane story has been around for a while now, and people say it's there, it's not there, it's here, it's gone, and so forth. Now it seems to be back for good. What about the chemicals? Is that more exciting? Doesn't seem to be.
It's the same story. It's the same story. You have more than one process that can explain those. So it's good to see them. It's exciting to see them. But as Vicky was mentioning, it's good to have also models to help us decide whether they are, biological or abiological. And right now, there is nothing that can help us really decide one way or another. And it's more complicated than that because it's not necessarily, one process or the other. It can be an or. So more data.
Well, this is a regrettable consequence of the fact that a lot of the biomarkers, correct me if I'm wrong, I'm frequently wrong, that many of the biomarkers are actually geomarkers too, that geology produces clues that are very similar to biology. So what would it take to figure out about, the true source of this methane? Just sending something to Mars that digs around in the dirt? How do you do it?
Hopefully you'll find an hydrothermal spring and little green stuff all around. That will be the best evidence that we can find. Intriguing is the seasonal aspect of it, but unfortunately life lives with season as well, but during the summer on Mars you also have a lot more ice that is sublimating, so maybe exposing more of the regolith and might be exposing more of the chemical that are producing those signatures. So it would take maybe something digging into the ground, getting closer to the source for identifying the source of methane. And I think we're getting closer and closer now. That requires more observations. But what I would like to see on Mars that is not exactly there yet is a series of environmental missions, environmental stations that will really look for those springs. Right now, we're just sniffing things around, whether remotely or with landers and rovers, but we need to go to those sources and we need to pin them down.
You want more ground truth. I mean, isn't this going to be a problem for you, Vicki? I mean, you look at the chemical composition of an exoplanet, and you find methane and oxygen. You've already talked a little bit about that. Oxygen by itself is not necessarily conclusive. Oxygen and methane maybe are not entirely conclusive either, even if you had both.
Yeah, that's certainly more conclusive, though. I mean, it does show. So, I mean, this is the thing. We often talk about disequilibria in environments, and they can be biosignatures, but not always. But really, what a disequilibrium is you look at a suite of gases and you say, that's funny. If you left these guys to their own devices, they wouldn't be in that arrangement. They'd be different products or different things in the environment. And what it's telling you is that the natural reactions that would have sort of washed this out are being countered by fluxes, so by gases coming off of the surface or whatever. If you can narrow down those fluxes, which is what they've done here with the methane in particular, if you can figure out what is being put out and how much of it is being put out, then you start to get an ability to figure out whether or not this is a biological or a geological source. And so we have to do the same thing on exoplanets. If we see a disequilibrium on exoplanets, we need to try and pin down, okay, using models, how much, for example, methane has to be coming out in the presence of this oxygen for us to be able to see it, because oxygen would destroy methane. And so this is really a case of anytime you see something like this, it's unexpected, it's intriguing, but you need to go right down into the details to figure out, how much of this stuff is coming off, is that something that volcanoes do, or is that, something anomalous that we don't understand? So it's an invitation to learn more.
It seems that every 6 months or so, there's another, apologies to the NASA people in the audience, but there's another NASA press conference to announce something that immediately the internet lights up. They're going to announce that they have finally found the Martians, and they haven't done so far. I want to ask this. Methane, of course, does not last very long. You throw a tank of methane onto Mars, and that means you can't heat leftovers with it the following weekend. But on the other hand, it also degrades in the Martian atmosphere because of the ultraviolet from the sun, right? So whatever it is that's producing this methane is continuing to produce it, right? And does that make sense geologically, if you assume that it's geological?
Yeah, it does. I don't know if you want to take
sorry, I
this,
asked
Vicky,
that.
but it does, because we have signs. We found evidence. There was a publication very recently of a very young, geologically speaking, volcanic activity in the Valles Marineris region. And less than 10 million year old is young at a geological scale, especially when you're using impact craters to actually give an age to a surface, which means that we don't know how young it is. So there is sign that water might be able to circulate at the surface of Mars. We have evidence for very young volcanic activity. So it might be that there is a source somewhere that's still venting.
So even if it's not biological, it suggests it may be an indirect pointer to biology because of the liquid water.
Yeah, if it's not biological, it could be a sign of habitability, which is exciting.
Yeah.
Jill, all this talk of microscopic life, and I think we've talked in the past about microbes that could do math. Didn't you consider that a mark of intelligence?
Well, our gut microbes are good at communicating.
Yeah, well, I said maybe algebra, but
Oh,
it didn't get a better reaction last time. Maybe they're not just biosignatures to be found with big optical telescopes, but also technosignatures. Have you thought of that? I mean, aside from using radio telescopes or looking for flashing laser beams and so forth, it's all this stuff gearing up to do astrobiology, you know, to assay the possible presence of microbial life somewhere. Could any of this find something that's clever enough to hold up its side of the conversation?
well, there are opportunities for finding technosignatures that aren't just radio or optical signals. If a technology is modifying the environment in gross ways, think of our geosynchronous belt, full of satellites. Maybe a more advanced technology would have this kind of thing on steroids. It's sometimes called the Clark exobelt because Arthur C. Clarke was the first person to hold the patent and understand geosynchronous satellite operation. So a planet that was distorted by this additional ring of debris or engineering architectures around it, which would have a different structure than a disk, might be something that we could see if it were transiting on ingress and egress, if we had high time resolution and very modest spatial resolution, we might be able to understand that whatever it was wasn't round. It had an appendage of some kind. And that might be a clue.
Could this be an explanation for what's going on with Tabby Star? It's just a geosynchronous, a fleet of geosynchronous satellites?
There would be more of a periodicity in that kind of a structure than you see in Tabby Star.
All right.
So that doesn't seem to work for that case.
Now, Jill, you're all too well aware of the fact that one of your colleagues actually made a bet with the public that we could find ET within 2 decades. But NASA's chief scientist about 2 years ago made a similar bet that we would find life in space. She was suitably nebulous about what that meant, but I think she meant life in the solar system. How do you all feel about this? Are we going to do this within? I mean, surely you get to ask this question at least 3 times a week.
Well, when I get an opportunity to talk to people, particularly young people, I like to bring up this very bold suggestion by Craig Venter and Daniel Cohen in 2004. They made a big point about the 20th century having been the century of physics and all of the progress that we made, quantum mechanics and the understanding of the evolution of the universe, the Big Bang. That was great, but what they said about the 21st century was that it was going to be the century of biology. And these 2 gentlemen were obviously talking about incredible progress in genomics and proteomics, and that certainly paid out even faster than they predicted. But I actually think that it's going to be the 21st century of biology on Earth and beyond. I think that within this century, we're going to know something about life beyond Earth because there are so many different ways of approaching it. The search for biomarkers in our solar system and various bodies, looking remotely, trying to sense the atmospheres of distant exoplanets, and looking for technosignatures, doing SETI in different ways.
Any young people in the audience who are studying physics, do not be discouraged by these comments. What about the other? By the way, I have to note this. When I look at the distribution of genes on this panel, the fact that there aren't too many Y chromosomes, you know, that wouldn't have surprised me at all 20 years ago, and it doesn't surprise me today either, and I think that's progress of a sort. Anyhow, what about the other 2 of you? What do you think? What do you you know, when people say, okay, you know, you're running all these models and this, that, and the other, but in the end, you don't want to just talk about Bigfoot, you want to find them.
Yes.
You know.
So I think it's very exciting because I think JWST, and I will word this very carefully, but JWST is our first opportunity to look for life on exoplanets. And we'll have to be incredibly lucky. We'll probably only get to observe 3 or 4 targets in detail, so we'd have to have that on there. But I think we're now entering this era where we are going to have the capability to start looking for molecules that would be very suggestive. It's probably not going to be a slam dunk, but it will be the beginning of our step in that direction. And I also want to say Proxima Centauri B was very exciting because the Europeans at the moment are looking at their very large telescope and coupling 2 instruments called SPHERE and ESPRESSO. And those 2 instruments, adaptive optics and high-resolution spectroscopy, may actually be able to detect O2 on Proxima Centauri B within the next 3 to 5 years. So, I mean, we are now getting to, and again, you know, my group would then tell you, okay, great, you found oxygen, fantastic. But, you know, are there any signs of an evaporated ocean or any of that kind of stuff? But still, being able to detect O2 on a planet orbiting the closest star to the sun, I think is, you know, the beginning of our journey. And I think that's going to happen, honestly, in the next 5 to 10 years, we will have that. So, hey.
All right. I hear you. I'll come back to that. This next question is for you, Natalie, but it's really designed to provoke John Rummel. But if you've been involved in choosing which parts of the Martian physiognomy we should be pawing over for signs of probably ancient life. So why aren't we doing that? Why do the rovers go around, you know, they're trying to understand the hydrology of Mars and chemical composition of Mars. But, you know, I talked to 6 people off the streets of Sunnyvale a week ago and asked them, how do you feel about the search for polycyclic aromatic hydrocarbons on Mars? And they all walked away from me. So, you know.
Now you understand why you're on that side of the stage and we're on this side of the stage.
I know there are many reasons. Okay, so, but my question is, why aren't we just sending something up there to look for life on Mars?
We're going to. All the missions you're talking about, well, you were not talking about missions, but this is where you were heading. We have been preparing those missions for a long time. Before you are searching for life, you need to understand what kind of habitat, what kind of habitability, what kind of habitat, and these are 2 very separate things you need to look for. You involve various scales. You need to understand processes. You need to understand the geology. You need to understand it's just like French cuisine. You need to have the recipe and you need to have the ingredients and to know whether the ingredients, you know, were in the proper proportions to make something happen. And it took us a number of years to do that. Now we know that Mars was habitable for life as we know it. And it's reasonable to think that something like our life could survive on Mars or could have evolved on Mars at the very beginning. You cannot just go to Mars and search for life. You need to understand what to look for. We sent Viking 40 years ago. It was a biological mission. And then we're still having a big question marks on the result because we didn't know the environment at that time. And we didn't know what could have produced the results we saw. So starting from then, we needed to understand the environment. And this is what Vicky is doing also with APL, trying to understand the environment of a planet so that we can understand the background of biology and just kind of extract the background and see if what we are seeing and what we are seeing is life or not. And you need to understand at what scale, what resolution you need to look at too. So this is what we have been doing for 40 years now. The next mission will start looking for biosignatures.
Yeah.
All right, this is a question for all of you.
I was going to say context is key. I mean, without context, you detect something, but you can't interpret it. You don't know what you're looking at. And that's what Viking discovered. So, yeah. So I think they're doing the right thing, Seth. Yeah. Thank you.
Rummel's looking askance. Okay, all of you, if someone wrote a check, I mean a big check, tomorrow to look for life nearby, but you could only go to one world in the solar system, what would that world be? I mean, we've heard a lot about Mars, but we've heard a little bit about Enceladus. Bill mentioned Enceladus, Titan. Now, I count 7 worlds, if you count the atmosphere of Venus, but 7 worlds elsewhere in the solar system that might potentially have a little bit of what was called by my astronomy professor dirty chemistry, revealing his interest in the search for life. Where would you go?
I jump for Enceladus. It seems to me that it's giving us an opportunity that's predictable to sample the contents of an ocean under ice. And it's it seems to me like a bit of a free lunch. I just don't want to pass up that opportunity. Nature is serving us up the contents of an ocean underneath the ice. Let's go see what's there. We don't have to figure out how to bore down, and it's being served up. Why don't we go try and
One
taste
vote
it?
for Enceladus. Any other worlds you want to champion?
I would vote for Enceladus too, but I think you're being chauvinistic, and I think you're just keeping us in the solar system. And I would want to go to TRAPPIST 1e. That's where I want to go. So.
I'm astounded anybody would accuse me of chauvinism. Okay, so you think we may find it on an exoplanet first?
I think exoplanets, I think Mars is a definite contender, but exoplanets may give you a run for your money as far as, well, mind you, Mars is already one, and they've already found methane, which is suggestive, right? But I think in the next 5 to 10 years, as I said, you're going to start seeing results from exoplanets that will be extremely exciting. And the thing I love about the TRAPPIST system is that even if we don't find life on those planets, this is just the whole suite of terrestrial planets all in a row, all different, it's like a scientist designed this experiment specifically to have these 7 planets all at different distances from their star so that we can understand how they all evolve under the influence of their star.
Don't you think they might have
Vicky,
infected one another if there's any
But
life?
Vicky,
Yeah.
what if they turn out to look exactly all the same?
I know, you've raised this before. So if they turn out to look exactly all the same, then yes, that's a technosignature, because somebody has modified them to be like, oh, we want all the planets to look like Earth, for example. If I looked at that system and they all looked, they all had surface oceans and they all had this clement surface temperature, then yes, I'd be very suspicious.
Yeah, could be a geological phenomenon that produces it. Okay, finally, just a quick take on the import of all this. In 1996, some of you may remember that, some NASA scientists, together with a gentleman here at Stanford, announced evidence for microscopic Martians in a meteorite. And as Chris McKay over at NASA Ames liked to say, there was no doubt that this meteorite was actually from Mars, because there was a brass plate on the bottom that said, "Made on Mars." Now, big headlines, but rather few people rioted in the streets. I mean, excepting the fans of European football. So, what's the possibility that people are going to get excited about this? How will the public view this? Oh, you found pond scum on Enceladus or Mars or, some nearby star, the star's planet. What's going to be the impact?
You want to take this? Okay. I think that finding microbial life will be extremely exciting, especially if it's a different genesis than ours. We only have 8 planets in the solar system. If it's a different genesis, then it tells you about the ability of life to arise in different environments. And that says something about the statistical chances that it is somewhere else. And the more you have of these little microbial guys everywhere, the greater the chance we will have to have intelligent life, because it's a lot easier to make simple thing than complex thing. But the more simple thing you have, the best chance you have to have complex thing as well. So microbial life is, in fact, talking to you about intelligent life.
Buying more lottery tickets.
Yeah, n equals 2 is the really important number here, either microbial or intelligent. Yeah. We know, good physicists, you count 1 to infinity. And we only have one example. It could be unique. The moment you find a second example, there are many. And so I think, as Nathalie said, finding a second example of an independent evolution of life, particularly within our own solar system, it means that's got to be ubiquitous out there.
Vicky?
Well, it'll tell us that we're not weird and we're not alone. So I think it'll answer 2 of the absolutely key questions, and I agree that the independent genesis idea, to know that when the conditions are right, life arises, that's incredibly powerful.
Okay, so there you have it. There's the promise. You can learn whether you're weird or not. Thanks to the panel, and thanks to our patient and attentive audience, and dessert is in the back.
Thank you, Seth.
Thank you indeed. Thanks, panel, and thank you, Seth. I was waiting for Seth to reply with, we're still going to be weird. But anyway, I'd like to just say a big thank you to Amy Himes from the SETI Institute for really quarterbacking the effort to organize this whole event this evening. And she was also supported by our Director of Communications, Rebecca McDonald, and Lee, who does so much of our graphic design and work, and other help from Michael Wiro and Erin Ferris, Laurie Marshall, who's not here this evening. But a lot of people put a lot of effort into tonight's program. I want to thank them all for this hard work. I think it's been a wonderful evening. And I want to take this opportunity one last time for us all to give a big round of applause to our 2018 award recipient for the Drake Award, Vicki Meadows.
Congratulations.